In the molecular world, interactions between molecules determine their behavior. These interactions are known as intermolecular forces. This is their story.
Order in the court! Today we are here to settle the case of which intermolecular force is the strongest.
Each force will present their case, arguing why they are the strongest, most significant, or most relevant to the chemical world. Prosecutor, please begin.
Thank you, Your Honor. Ladies and gentlemen of the jury, intermolecular forces are the interactions that occur between molecules, indicating their physical properties, including viscosity, boiling point, and solubility. Within a molecule, atoms can make covalent and ionic bonds with each other, but molecules can also form interactions with other molecules. These are the IMFs that we will be investigating today. We will be hearing from our main forces, ion-ion, ion-dipole, dipole-dipole, hydrogen bonding, and London dispersion forces. Let's call in our first witness, ion-ion. Mr. Ion-ion, can you tell the court about your interactions?
Absolutely. I am the strongest IMF because I involve full formal charges. I hold ionic compounds like sodium chloride together in a crystal lattice. It takes immense energy to break us apart. Without me, ionic compounds would fall apart entirely.
Impressive. But can you tell us what your effects are on physical properties?
I have very high melting points and a very low vapor pressure. Breaking my bonds takes serious energy.
Noted. Next witness, please.
Ion-dipole, you're up. How do you compare to ion-ion? Look, I may not be as strong, but I play a critical role in solutions. When ionic compounds dissolve in water, I step in. Sodium ions are drawn to the oxygen end of water, while chloride ions are attracted to hydrogen. This makes me crucial for solubility.
Can you elaborate on solubility?
Well, I guess you could think about it like dissolves like. Polar molecules dissolve in polar solvents due to interactions like mine. In ionic compounds such as sodium chloride, the molecules dissolve because I mediate the attraction between ions and water molecules. Without me, salt wouldn't dissolve in water, and, I guess, life wouldn't exist.
Dipole-dipole, please tell us about your interactions.
I exist between polar molecules. For instance, in hydrogen chloride, my partially positive hydrogen interacts with another molecule's partially negative chlorine. Although I may not be as strong as the ion-based forces, I still play a significant role in boiling point and solubility.
But isn't it true you're only limited to polar molecules?
Yes, but polar molecules are everywhere, so I'm still highly relevant.
What about your viscosity?
Strong IMFs like mine make liquids more viscous because our molecules are held more tightly together. But as temperature increases, the viscosity decreases because the interactions are weakened.
Hydrogen bonds, please present your case.
I'm no ordinary dipole-dipole interaction. When hydrogen bonds with highly electronegative atoms such as fluorine, oxygen, or nitrogen, I create an exceptionally strong dipole. This gives water its exceptionally high boiling point and surface tension.
Okay, well how do you influence surface tension?
Molecules at the surface of water pull inward due to my strength, creating surface tension that allows water to form droplets.
LDFs, why are you here? Aren't you the weakest IMF?
True, but I'm universal. Even nonpolar molecules, including hydrocarbons, depend on me. I create temporary dipoles when electron clouds shift. The larger the molecule, the stronger I become due to increased polarizability.
But doesn't your weakness limit you?
Not at all. Without me, nonpolar substances wouldn't exist in solid or liquid form.
Okay, but how do you relate to vapor pressure?
Weaker IMFs like me allow molecules to shift into the gas phase more easily, resulting in a higher vapor pressure.
Your Honor, as we've heard, every IMF plays a vital role.
Ion-ion dominates ionic compounds. Ion-dipole facilitates solubility. Dipole-dipole governs polar molecules. Hydrogen bonding creates sustaining life properties. And LDFs hold nonpolar molecules together. Together, these forces determine boiling points, melting points, solubility, and much more. Our molecules today taught us that stronger IMFs lead to higher boiling points and lower vapor pressures, while weaker IMFs generate greater volatility. Pressure also plays a role. Higher pressure encourages phase changes in substances with strong IMFs. Let's not also forget about the forces like metallic solids with their sea of delocalized electrons. Making metals malleable or covalent network solids like a diamond, where rigid lattices give unparalleled hardness. Based on the testimony, it's clear. All IMFs are essential. Court is adjourned.